And our flipped classroom begins. All right, so the goal of this lesson is to be able to graph a square root and a cube root function. That's the main goal, to be able to make a quick sketch. But you also need to really understand the domain and range. Before you get into calculus, and I mean really into calculus, you need to know a list of functions and their domains and ranges. Okay, and we'll, as we kind of roll through the trigonometry and as we roll through pre-calculus, we'll see why it's so important to know the domain of every function, to really know it, and to really know the range. Now, domain, just a reminder, my hope is that word comes back. The domain is every single input of a function. It's all of your x values. It's all the numbers that you can plug into a function, and the range is every possible output. And the nice thing is the square root function might be the first time that those two concepts are deeply understood, because it lends itself to studying domain and range. The domain is not all real numbers. It's never all real numbers for a square root function. And the range is also never all real numbers. So it kind of forces you to really think about what domain and range are as concepts. So you're going to have to be able to graph a square root function and know its domain and range. You're going to graph a cube root function and know its domain and range, and then just to know the general nature of the graph. All right, be able to know quickly, oh, the graph is kind of over here, and this is what the shape kind of looks like. So it's to have a decent idea of the graph as a rough sketch. All right, so graphing radical functions. The radical function exists as an inverse function, just like the opposite of adding is subtracting. The opposite of raising something to the second power is taking a square root. Okay, so really conceptually, wow, pretend that's a square. Conceptually, 5 times 5 has an area of 25, right? If you have a 5 by 5 tile of whatever unit of length, the inside is going to have 25 squares, right? 5 squared is 25. Well, what's the inverse of that? What if there are 25 squares? What's the side length of the square? It's 5. So the square root function is an invention as an inverse of x squared. So just to circle it, and we'll discuss the graph a little bit more later, but the opposite of x squared is the square root function. But the square root function as an inverse is not a function, so this is where it gets kind of ugly. All right, if you invert the x squared function, you get a curve that is not a function. It does not pass the vertical line test. So the square root function is just a piece of the inverse of x squared. Let me show you that in blue. If I take just half of x squared, I'm going to draw it in blue here, just the positive half of x squared, and I invert it, and I swap x and y, I will get a graph that looks just like the top portion here. I'm crossing out this portion, so I just want you guys to know. Remember, the goal here is to know that the original square root function looks kind of like, drawing it off to the side, kind of like a little hook that flattens out. Okay, so that's the nature of the square root function. Okay, you'll spend a lot more time with inverses later. You'll spend time discussing that in detail, even in calculus. Okay, and then similarly, if you have the cubic function, so the original x to the third power function, I'm sketching in blue. That's your cubic function. Okay, x to the third power is blue, and if you invert that, if you swap all the x's and the y's, you get a function that looks like it's, instead of growing quickly, it's growing very slowly, but it goes left and right forever. Okay, so the cube root function in red actually goes left forever, and it goes right forever, it goes down forever, it goes up forever. So the domain and range of the cubic and therefore its inverse, not very interesting. We're going to see an example of that. But the square root function has an interesting domain and an interesting range, and then we're going to spend some time on that. Okay? So right now, here's what you know. The cube root function generally looks like this, where something interesting is happening at the origin, and the original square root function over here starts at the origin, whatever that means, and goes up and to the right and flattens out. So kind of that's where we are for now, and we'll see some examples. Okay? So that takes us to our Desmos demonstration. Boop. So here's our Desmos demonstration. Okay, so let me move that camera around a little bit. Right, so I have and using function notation, I have f of x equals the square root of x programmed into Desmos, and you can type that into Desmos. I use f of x notation just because that's important. So I just want you guys to see, you can actually see Desmos will give you that same shape. All right, and just to be a little bit more clear, I want you guys to see that if I type f of 0, so if you actually plug 0 into that function, f of 0 is 0, which means the square root of 0 is 0. And I see that in the graph right here. The square root of 0 is 0. Okay? Now, let me delete this and delete that. What if I change the input to 1? What's the square root of 1? Well, the square root of 1, oh, let me change that. So the square root of 1 is 1. So the square root of 1 is 1, and there's my point. The square root of 1 is 1. What if I want to take the square root of 2? The square root of 2 is a decimal, right? Square root of 3 is a decimal. You get these irrational numbers, but the square root of 4, you plug 4 into the function. The square root of 4 is 2. So the square root of 4 is 2, and there it is. And then I'll do one more, find one more value. The square root of the next perfect square is 9, so the square root of 9 is 3. So when my x value is 9, my y value is 3. Okay? So let's go back to our square root function, and we'll do a demo of the cube root function as well. So it's important, and I'm going to color code these to know that the original function, the original square root function, you can find points on it all day long, but the important points are the square root of 0 is 0, the square root of 1 is 1, the square root of 4 is 2, and the square root of 9 is 3. And in between every one of those x values, there is a y value. It's just not a very nice number. So the function looks like this. The square root of 0 is 0. That's my first point. 1, 1 is on my graph. 4, 2 is on my graph. And 9, 3 is on my graph. And infinitely many more points, but my curve looks like that. And I sketched that terribly. Hopefully you'll do a better job than I just did. But the function rises quickly initially, and then flattens out, flattens out, flattens out, flattens out. It never stops going up, but it goes up at a slower and slower and slower rate. We're getting into the calculus of it, but that's okay. So I do want you to see one example of a function that is also a square root function. Okay, I'm going to make this one blue to color coordinate it with G. So G is going to be blue. G can be a little strange, so I just want to kind of you to see this. Okay, if I plug in 0, if I actually plug in 0, I get the square root of 0 minus 3. So this actually becomes the square root of 0 minus 3, which is error. Okay, and I want you to see in Desmos why that's the case. So if I change that to x, pull up my keyboard, x minus 3, close all that out. The function is now starting at 3, 0. Okay, so this goes back to those transformations that you've seen with multiple functions at this point. When you subtract 3 from x, it actually shifts the graph not to the left, which is kind of intuitive. It actually shifts the function to the right. Okay, so let's look at that numerically. I plug in 0, I get an error message. I plug in 1. The square root of 1 minus 3 is a negative. There is no square root of a negative. Okay? So I'm going to get error messages until I plug in 3. So 3 minus 3 is 0. The square root of 0 is 0, which takes me here. And the beauty of this is the relationship between these two functions is the blue function, g, the graph, is going to be 3 spaces to the right of the original function. So I can actually take each of these points that I've already found and shift them 3 spaces to the right, 3 spaces to the right, and you see the exact same curve shifted 3 spaces to the right. And let's test it out. Let's find this. Let's plug in 4. So I'm basically taking every one of these x values, and when you move a point to the right, you're really adding 3. And it's kind of weird. We're actually adding 3 so that we can see the relationship. So let's plug 4 in. 4 minus 3 is 1. The square root of 1 is 1. Okay? Now I want x minus 3 to be a perfect square. So what does x minus 3 need to be so that I get out 4? It needs to be 7. 7 minus 3 is 4. The square root of 4 is 2. Okay? We can play numerical games like this, but you don't have to be able to play those numerical games. You just need to know the general form of that curve. Okay? And there's a shortcut for that numerically I'll show you in a minute. Okay? So that is the square root function and the domain. So let's not forget to discuss the domain. The domain of the original square root function is, in red, the original domain is all x values greater than or equal to 0. Okay, so the domain starts at 0 and moves to the right forever. Okay, another way to write that is in interval notation. 0 is included, comma, all the way to infinity. All right, so that's the original domain, 0 to infinity, 0 and to the right forever. So just remember the domain is all x values. The range, the original range, the range of the original square root function, the parent graph, is going to be all y values greater than or equal to 0, or also 0 and up forever. This curve goes up forever, so it includes all y values above 0. Okay? Now, let's do that for the g function in blue. Okay, so now this function has a different domain, so I'm going to write it up top. The domain. So the domain of this function is left to right. Remember, domain is x values, so graphically you're looking left to right. The domain starts at 3, and then it moves to the right forever. So the domain is all x values greater than or equal to 3, or 3, bracket means included, comma, infinity, meaning all numbers between 3 and infinity, including 3. So 3 to infinity. And then the range, this is where it gets kind of weird. So the range is your y value. Well, your y value here is still 0. So the range is 0, and then it moves up forever. So the range is going to be 0 to infinity, or you can write that as y is greater than or equal to 0. Okay, and we're going to do other examples of that. So, just to reiterate, the goal of this lesson is what's the general nature of a square root function? What does it look like? And then what's the domain and what's the range? And that all kind of centers around this point here. This point here. Okay? All right, so let's look at a couple more square root functions. Okay, so here's the pattern I want you to see. If the function is of the form, so I'm going to jump straight to, it's all about this. It's all about hk. X minus h, h is the x coordinate, k is the y coordinate. I want you to see that when you look at a square root function. So I'm going to graph f is going to be purple. So h in this problem is going to be 3. Remember, when you see minus h in a formula, then you think opposite. So when you see minus 3, that means the point 3 is kind of important. When you see minus 4, k is plus k means whatever you see is what you see. So here we change, here we keep 3, negative 4, 3, negative 4 takes me here. Okay? So the general form of that function is going to be up and to the right from that point. Okay? And I'm going to take you to Desmos to kind of demonstrate that. So we have x minus 3 minus 4, and that takes me here. So you see the point 3 and negative 4, 3 and negative 4 is really where the function begins. So you want to think that 3 and that negative 4 has something to do with the domain, all values left to right, all of your x values, and it has something to do with range, which are all of your y values, bottom to top. Okay, so let's go back. Oh, that's not it. Okay, so for this particular function, the domain is going to be 3, and it goes to the right. So the domain is going to be all numbers greater than or equal to 3. So for the purple function, the domain is going to be all x values greater than or equal to 3, or you can write that using interval notation. Okay? And the range of the purple graph, how low does it go? It goes down to negative 4, but then it goes up forever. So from negative 4 up to infinity. So the domain is all y values greater than or equal to negative 4, or negative 4 to infinity. Okay? So that is F. Let's look at G. G, we're looking for a pattern. The only difference is that minus sign. So now the question is, what does graphically, what does changing the sign of the function rule itself due to a graph? And you've seen this with quadratics, you've seen this with lines, slopes. It actually reflects over the x-axis. So let's go to Desmos to double check. When I put that negative in front, so let's look at the original graph. Now the original graph is here at 3, negative 4, and it's going up and to the right. Let's see what happens when I put that negative sign in there. Quick demo. So I'm going to put that negative in front, and let's see what happened. Yes, it was 3, negative 4, and up and to the right. Now it's going down and to the right. So the graph was here, was going up and to the right, and now it's going down and to the right. But that point, that 3, negative 4, did not change. So so that's purple. Let's use orange. So I'm going to graph G using orange. 3, negative 4, still important. Still has something to do with my domain and range. So let me move my head out of the way. Scoop. So 3 and negative 4 here. But we have now reflected the graph, so now the graph is going down and to the right. So let's find the domain. The domain is still 3 to infinity. So the domain is still all x values greater than or equal to 3. So the domain did not change. 3 to infinity, but the range did. And I'm going to put this bold, put it in a darker color, because this is where most mistakes happen when people write the range. The range. All right, the range is going to be bottom to top. So you can either say all y values less than or equal to -4, okay? Or, here's where you have to be careful. This arrow is going down, right? So now you're thinking about the y values as going from bottom to top. So you've got to think of it as from -infinity to -4, including -4. So range, just to be clear, in interval notation, range is always bottom to top. With the purple graph, the bottom was -4 and the top was infinity. So we had -4 up to infinity. Well, now, since the graph is going down, we have bottom -infinity up to -4. So the order matters there. So be careful when you write a handwritten quiz or test. If the curve is going down, -infinity is where you begin your interval notation. Okay? And then one last one just for clarity. Let's go red. Bow! So I'm going to graph H. In red, H is 3, K is 2, 3, 2. This particular function does not have a minus in front, so it has not been reflected. So that's the general shape of the graph. The domain is going to be 3 to infinity. And the range is going to be bottom to top, which is 2 to infinity. Okay? All right, so we've spent most of our time on a square root function for a reason. It's the tricky one. The domain, you notice, the domain is never all real numbers. It's always h to infinity. Or if I reflect over the y-axis, but we're not going to be reflecting over the y-axis right now. So in general, this curve starts somewhere and blasts off to infinity, okay, for domain. The range could be -infinity up to that y value where it starts, or it could be that y value where it starts up to infinity. So those are your two cases for range. All right. Cube root function. Much easier to graph. Bow. So I'm going to graph the original cube root function. I'm going to go to Desmos. I'm going to pull that up. The original cube root function is right here. The cube root of x looks like this. So just to be clear, the cube root of 0 is 0. Okay, so this is what the graph looks like. Let's actually find a few points, one time and one time only. So I'm going to put 0 in the middle. The cube root of 0 is just 0. So the point 0, 0 is here. The cube root of 1. The cube root of 1 is 1. So 1, 1. So far it looks like the square root function. But then I'm going to jump ahead, way ahead for a reason, just to make a nice and clean number. The cube root of 8 is 2 because 2 to the third power is 8. That's how you're thinking about it. The third root of 8 is 2 because 2 to the third power is 8. Remember, the opposite. The inverse of cube root is to the third power. So if I put 8 in and I get out 2, that means if I put in 2, I get 8 in the cubic function. So those are inverses. Okay, so you're kind of thinking backwards. Now you can let the calculator do the work for you, but that's conceptually what's going on. So far we've plugged in 8. When you plug 8 in, you get out 2. So this curve looks like the square root function, but it's actually getting flatter even faster. So it looks like a squashed square root function, but the cube root function behaves nicer as a graph. Here's what I mean by that. The cube root of -1 actually exists as -1 because -1 to the third power is -1. So the cube root of -1 is -1. The cube root of -8 is -2. So let me write that out. The cube root of -8 is -2 because -2 to the third power is -8. So -8, -2, and the curve flattens out this way. Okay, so it gets kind of steep. It starts to grow quickly, and then it flattens back out. So you have this kind of weirdness going on around 0. So just to say that again, the curve is pretty flat, it's pretty flat, it's pretty flat. Then it grows quickly between -1 and 1, but then it flattens back out. That is the original cube root function. Now, just to kind of see the same pattern we saw with the square root function, let's see what happens here. Okay. So I'm going to look at Desmos just to kind of get a visual on this, but it looks like h is 2. So it looks like I'm going to take that original point, 0, 0, and I'm going to shift it 2 spaces to the right, just like we did before, but since there's no number out here that I'm adding or subtracting, it doesn't look like I'm going to shift it up or down. So let's go back to Desmos. And remember, this is very cursory. I just want you to kind of have a general shape of the graph. So I'm going to put, so here's my original graph. I'm going to put a 2 in front. So let me open up the keyboard. 2 in front under the radical. So under the radical, I want to write -2. And let's close that out. So -2, yes. So here's what happened to Desmos. X minus 2 shifted that original point at the origin 2 spaces to the right, and then multiplying by 2 on the outside stretched the curve. The curve was originally flatter. It was originally flat, and multiplying by 2 made every point twice as tall with respect to its distance from the x-axis. Okay, so if I take that 2 out, you see it flatten back out. So this distance from here, let's say from 6 to here, is just under 2. Let's find where it's 2. 10 goes to 2. That's 2 spaces away, right? I'm going to see what happens when I put that 2 in front. Now it goes to 10 goes up to 4. So by multiplying by 2 on the outside, all of the points get pulled farther away from the x-axis. It literally vertically stretches. Okay, so you do need to know that when you multiply a function by any number greater than 1, you're going to vertically stretch the function. Okay, and you saw that with other functions in the past. Okay, so back to my PowerPoint. So all you need to be able to do is go to Desmos or a graphing calculator and find a few points on the graph. So 2, 0 is on my graph. It looks like 10 goes to 4. It looks like 3 goes to 2. So 3 goes to 2. So let me go back. When x is 3, the y value is 2. So I have this portion of the graph. And then 1 will go to -2, but let's make sure. 1 goes to -2, so the point 1, -2 is on my graph. 1 goes to -2. Okay, so I can find a few points. But here's why I say the cube root function is not very interesting. So the blue function g has a domain of, it goes to the right forever, it goes to the left forever, and there are no gaps. It's a continuous function. So the domain is all real numbers, or you can write negative infinity to infinity. The range is also up forever, down forever, down forever, up forever. So the range is also all real numbers or negative infinity to infinity. Don't forget your parentheses. You never put a hard bracket on infinity or negative infinity. That bracket means inclusive, and you never make it to infinity. So when you say infinity, you mean without boundary to the, in this case, this means without boundary to the right, meaning the x values can get as large as you want them to. Negative infinity means you can go left, x can be as small as you want it to, or as far away from 0 to the left as you want it to be, etc. So that's it with cube roots. Not doing a lot with cube roots. Okay, last but not least, boop, you do need to know how h affects your graph. Okay, x minus h. H is going to shift your graph left or right. Okay, and there's an example over here. When you see x minus 2, that's going to shift your graph to the right. When you see x plus 1, that's going to shift you to the left. Okay, k on the outside behaves more intuitively. When you add 3 on the outside of any function, that's going to shift you up. And when you subtract 4 on the outside, that's going to shift you down. So k is the easiest and most basic of transformations. Vertical translation or shift up or down. All right, inside the function, you have a horizontal, meaning left or right. Okay, shift. And then a on the outside. We saw it briefly, but I do want to make it clear. Two things are happening with a. A, okay? A is that coefficient out front. When a is negative, and that's the only one we're going to focus on. When a is negative, you reflect over the x-axis. So it was going up to the right, now it's going down and to the right. And we saw an example of that. And then you have a vertical stretch. When a is greater than 1, so let me write that. When a, and I really should say the absolute value of a, is greater than 1. Okay? So whether it's 6 or negative 6, you are vertically stretching it. Now, if it's negative 6, you have two transformations. If it's negative 6, you're going to stretch it, but you're also going to reflect it over the x-axis. Okay? So regardless of sign, if you multiply by 6 or negative 6, you're stretching it. But if you're multiplying by negative 6, you're also reflecting it. And then what we did not talk about, when you multiply by a number between 0 and 1, so let me write that out. When a is between 0 and 1, not including 0, let me change that. So when you're between 0 and 1, a fraction or a decimal, a proper fraction, then you're going to compress or shrink the graph. You're going to make it look even flatter. Okay? So these are going to make the graph behave the same way in terms of domain and range. They're just going to make the graph either grow quicker or grow slower, but it won't affect the actual domain. So I'm going to leave this for you as kind of a challenge. If you want to write a general rule for domain for any function of this form and range for any function of this form. Bonus, if you made it to 34 minutes, that's a long video, guys, I know, I talk a lot. So if you can, give me the generalized domain and range, meaning the domain and range for any function of this form, and I'm talking about exact now, bonus points. And we can debate how many bonus points. I'm going to tell you this. The domain depends on h and a. The range depends on k and a. If you can tell me what the domain of any g is and the range of any function g is based on that equation, bonus. I'm going to leave it at that. Watch this, take good notes, and be ready to work on this Thursday and Friday in class. All right, over and out.